And I'm going to give you an informal definition. There's a longer definition to it. You'll definitely learn it if you're in calculus. There's like 3 parts to it, but the basic idea behind continuity of a graph is if you can sketch the graph without lifting your pencil. So if I give you something that looks like this and I say, okay, start sketching the graph, and you're like, start on the left, and you're like, yeah, I'm pretty good. I'm not lifting up my pencil. You have continuity. So as an informal definition, if you can sketch the graph without lifting your pencil, then you have beautiful continuity. Now, of course, along with that comes this idea of, well, then what does it mean to be not continuous, or discontinuity is what we call it in math. Discontinuity. So let me just draw you some examples of what it means to be discontinuous. So if you had something like that, you have this, what's known as a piecewise function. So you have this function, there's a hole here, then you have to jump up. If you had to lift your pencil, again, if I was going to trace this from the left to the right, I'd have to lift my pencil up in order to go this way. And that's not continuous. You could also have graphs where looks like this. You like have a hook here and a hook here. And so again, if I were to start drawing this from the left to the right, I would have to eventually, I mean, my pencil's going to go up and up and up. I'd have to lift my pencil over down here to start drawing that side. So that also is discontinuous. So the first part on the MyMathLab homework will say to you, determine intervals of continuity on the x-axis. And this is important. You always do continuity along the x-axis. It's never along the y, it's always along the x. It's similar to like domain of the function, so continuity. And let me give you just some pictures here, some graphs. Good old parabola. Good old line with a hole in it. And we'll do this one. Hopefully you can understand what I'm drawing here. So determine the intervals of continuity. So this parabola, we talked about that before, is if I start on the left, I can keep going. I have no problem tracing it whatsoever. There's no jumps, there's no holes. I never have to lift my pencil. So along the x-axis, I have no problems whatsoever. My continuity is from negative infinity to infinity. I'm totally fine. It's continuous the whole entire time along the x-axis. This one, so let's see if I'm traveling. Uh-oh. Again, don't go to the y, go to the x-axis. We have a problem right here. I shouldn't have done that. I don't like doing that. But this number is 3, right? So at 3 on the x, I have a problem. And then I'm good after that. My pencil doesn't have to lift up, only at 3 on the x. So I'm continuous from negative infinity up until, where's my first problem at? 3 on the x. And then I'm good after 3. So I would say united with 3 to positive infinity. Remember all interval notation? We're doing that again. We want to make sure we always have a low bound, up bound, low bound, up bound. It needs to go in an order. So this one with the hole in it, you could have pieces of continuity. That's fine. So it's continuous from negative infinity along the x up until the problem area. I have a hole at 3. This one with an asymptote, where your pencil, if you were to start drawing this, would just keep going up and up and up and up. Well, it's still continuous on this side. It's continuous up until this point right here, this asymptote, which is located at 2 on the x. So again, I would say this is continuous from, I'm good from negative infinity up until 2. And then I'm good after that. I'm good from 2. I can get really close and then come on down to positive infinity. So that'll be the first part of your homework, this idea of continuous. And it's always, always, always along the x-axis. And you always start from the leftmost x. So if this graph had stopped here, then you would have a lower bound that would be 4 or something, like -4. But since our graphs are continuing, we're going to always start at negative infinity and end at negative infinity for these continuous graphs here. All right, so that's continuity. And you'll have, like I said, they'll give you some pictures. You'll have to determine where it's continuous. Now we're going to talk about increasing and decreasing. Because again, this is all the ideas behind what you're going to need for if you take calculus. You have to understand where it's continuous, where's the function increasing, where's the function decreasing. And so we're going to do that next here. So let's see. Increasing and decreasing on the open interval. Increasing and decreasing on the open interval. And this is nice right here, this word open interval, because all of your interval notation is going to be open, meaning it's going to have just parentheses. You don't ever have to worry about brackets. Now, increasing and decreasing is also on the x-axis. You don't use y values. You're only worried about the x-axis. And just like continuity, you read a book, just like you read a book, You got to start on the left and go to the right. Okay, so I am going to sketch a little graph right here, and then we're going to talk about where it is increasing and decreasing. Hold on while I count how many things I have. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. And I got hopefully you can see this. Trying to draw that a little bit better because they're going to give you a graph just like I'm giving right now. And so from this graph, you have to tell me where's the function increasing, where's the function decreasing, and where's the function constant. And you, again, always tell me along the x-axis. Never, ever tell me along the y's. Tell me along here. So if I start on the left, left. Left, left, left. What is my pencil doing as I go to the left? Going down, right? It's decreasing. So I am decreasing from where? Well, even though it looks like I'm decreasing from a positive infinity, that everybody always gets that confused. No, that's why. We're along the x-axis. I'm on the negative side of x. So I'm decreasing from negative infinity up to this point. This point right here, what is that point on the x? Well, that's the point -2. And then what happens after that? Well, then it looks like my pen goes up until about where? Probably about right here. Well, what is that along the x? That's 1. This was -2. So from -2 to 1, I'm increasing. So notice again, it's always low, high, low, high. And it goes in order and it always repeats itself. And all of these are open. All of these are open. Don't put a bracket. It's all open. So it's going to be really nice for you. Then what happens after 1? Well, it looks like I go down again. I go down until where? Well, this would be 2 on the x. So I'm decreasing. So again, I'll put it right here. You can put a united. I'm decreasing again from 1 to 2. And then what happens after that? Looks like I'm straight. I'm constant. I am constant the entire time along the x-axis after the point 2. So I am constant from 2 on the x-axis all the way to the positive side. So again, just to go through that, I'm going down, decreasing from negative infinity up to -2. Then I increase from -2 is my starting point to 1. Then I decrease again. So I'm going to put some extra information along this side. Decrease again from 1 to 2. And then I have a constant after 2. And they're going to do this. They're going to put a bunch of little, hills and valleys in it and then constants. So you need to just make sure you're taking it from the left to the right on the x-axis and leave everything open. And you should be good to go. Okay. Now I'm going to go through 7 different parent functions, which I'm sure you've seen before. We just want to go over them again, make sure you're familiar with them, because that's going to lead us into what we do in most of chapter 2. But I am going to list them all out for you. And then we're also going to talk about their domain and range. List of parent functions. Okay, so the first one is what we just did up there, your constant function. And I'm just going to give you an example of the constant function. I'm going to underline it. F of x equals 2, y equals 2. So if y equals 2, it's always, always, always a horizontal line. So you would have a graph, you'd go to 2 on the y, and you'd be constant the whole entire time. Now you have to tell me what your domain and range are. We got to go back over that again. So we're going to do that real quick. Domain, how wide is this function getting along the x-axis? Well, it's going from negative infinity to infinity. But the range, how tall is this thing? Well, this only has values of 2. That's it. My y's are always going to be 2. So you write 2. And this time we are using brackets and parentheses and both of them because we're talking about domain and range. So that's the constant function. Number 2 is good old identity function. And the identity function is when f of x just equals x or y equals x line. And it looks like this. It goes through the origin and always goes up 1 over 1, up 1 over 1, or down left, down left. That's the identity function. Okay. So if I asked you, okay, what would be the domain? How wide is this graph going to get along the x-axis? Well, it too is going from negative infinity to infinity. It's going to go along the x-axis the entire time. How tall is this thing going to get? Well, my hands would have to keep going up and going down at the same time. So the range would also be negative infinity to infinity. So there's your two basic lines that we'll have for functions. The third one, also a famous one, is the squaring function. They call it squaring. I call it quadratic function. But it's f of x equals x squared. And so for this f of x equals x squared is good old parabola. That's 0, and then it goes 1, 1, negative 1, 1. It goes 2, 4, 1, 2, 3, 4. Negative 2, 4. It always has symmetry to it. So if I want to talk about the domain of this one, how wide is this thing getting? Again, along the x-axis, what x values can I plug in? I can plug in all of them. Negative infinity to infinity. The range, however, how tall is this thing getting? Well, it starts here on the y and then goes up. Range, remember, is along the y-axis. There's no picture down here. There's nothing below 0. But I do have y values that are above 0. So I have values for y that are 0 and above, 0 to infinity. That would be your basic parabola. And again, these domain and range are going to change slightly. Well, the range will. For a parabola, the domain will always be negative infinity to infinity. Always, always, always. For a parabola. But the range will change depending on where we shift it. If we shift it up or down, it's going to have a different range. But the domain would remain the same. So that's a squaring function. Then we have a cubic or a cubing function. So f of x equals x cubed. And this one looks like, goes through 0, 0, and it kind of like goes down and curves. It does this little slight curve and then comes up. So I know it's going to look like that it's just going straight, but it actually is curving ever so slightly. So if I asked you, can I use every x along the domain? You sure can. Your domain is negative infinity to infinity. What about my range? How tall is this thing getting? Well, if these arrows are going up and down, this thing is going up and down the whole entire time. Negative infinity to infinity. All right, so there's your first 4. Constant, identity, squaring, and cubing function, or quadratic and cubic is what I say, but no problem there. Now we'll do the last 3. This is the square root function. And this one would be like f of x, this would be your parent, equals the square root of x. And so this one looks like this. If you can take the square root of 0, 0, that's totally fine. Square root of 1 is 1. Square root of 2 is a decimal. The next one that has a whole number is 4. The square root of 4 is 2. So it kind of like shoots off like this. It curves off to the side. So I have a different domain here for Mr. Square Root, okay? Think about it logically. I mean, you can't take a square root of a negative. I've been teaching this all day to my students, but you can't take a square root of -4. I mean, yes, you've learned i's probably in the past, but we're not talking about that. We're talking about domain. What are the x's on this x-axis that I can plug in? Man, I am not recording this now that I realize something. Give me 1 second while I hit record. Oh, recording has started. Somebody did it for me. Brilliant people. Thank you so much, whoever did it for me. So the domain, how wide is this? This thing is only from here to the right. And what's that point on the x? Well, that's 0. So my domain is from 0 all the way to the right, all the way to infinity. My range, how tall is this thing getting? And again, even though it looks like it's curving here and you're like, oh, it's going to stop right about 2 point something. No, it doesn't. It doesn't stop because again, if you put in 100, you would have 10. If you put in, you know, 1,000,000, you would have a very large y value. So your range would be from 0 on up. It would be the same. Does that always happen? No, again, it depends on if we add 1 on the outside or if we add 1 in the middle or something. Things will change when we start adding numbers to it. But just so you know, your basic parent function, this is domain and range. So then there's square root function. What about cube root function? That would be f of x equals the cube root of x, or x to a fractional power. We'll get to that. So cube root function kind of looks like the cube one, the one that went down through the middle and up, except this time it goes like sideways. Still goes through the middle. And again, it kind of looks like these are flat, but really they'll keep ever so slightly curving. So your domain, how wide is this thing? Obviously, it's going to go negative infinity to infinity. Range, again, they're not an asymptote here. They're actually just going to keep going, curving ever so slightly. So this thing will keep getting pretty tall if you zoom on out. Negative infinity to infinity. All right, and then the last one is the absolute value function. And this function is f of x equals the absolute value of x. Now, if you didn't know, your calculator has the absolute value function on it, just to show you where it's at, and I'll type it for you. So it's located in this word math right here on your calculator. Hit the math button. Go over to where it says num, and that first thing that comes up, abs. And then type in x, math num abs. And you can write that down if you want to. Math num abs. That's where it is located on the graphing calculator. And what it looks like, zoom 6, it's a V. So it's a V-shaped graph. And I'm going to do something for you which hopefully won't scare you too much, but I'm going to separate this into a piecewise function. And I'm doing that for a reason. It'll become important and helpful later. But if you were to cover this side up right here. This really is the identity function. It starts at 0, 0, it goes up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. So this is really, on the right side, x. On the left side, sorry for the glare, this is the identity function, but opposite, and it would be negative x. And so this would be when x is bigger than or equal to 0. Whereas the other side is when x is less than 0. And that would be what you could graph. You could actually write an absolute value as what's called a piecewise. Don't freak out yet. We'll get to them in a minute, but this is your v function. You go up 1 over 1. And this side would be the x side. And this side would be the negative x side. Kind of neat and interesting. So, but let's talk about the domain. The domain, how wide is this thing going to get? Well, it's going to go on and on and on and on. So along the x-axis, negative infinity to infinity. Range, similar to the parabola. It doesn't have anything below 0, so it's everything from 0 for the y values on up. So from 0 all the way to positive infinity. Okay, so just did a lot there, just making sure before we move on, no one has any questions. We've covered continuity. Continuity is along the x-axis. Are you continuous? Do you have any jumps? If you have a jump, you put it in your interval. If you're smooth the entire time, you're continuous negative infinity to infinity. If you got a jump, you're negative infinity up to what point is that? 3, and then 3 to infinity. If you got an asymptote, negative infinity up to 2, 2 to infinity. It's always along the x-axis. And then increasing and decreasing and constant functions. Those are also along the x-axis. What's your pencil doing? Is it going down or is it going up? It's going down. It's decreasing. From negative infinity up to where on the x? Then it increases. From where to where? Think of it like you're reading a book. And then we just went through all the parent functions, which you need to familiarize yourself with. Constant, identity, the squaring one, the cubic one, and what it looks like. The square root, the cube root, and the absolute value. Okay, and then we're going to end our lesson on symmetry. A few questions on your homework will be on symmetry. Remember, this is homework number 4. This one right here. All of this will be in one homework section. There are 3 types of symmetry. All right, move this up. So the first type of symmetry is you could be symmetric along the y-axis. Y-axis symmetry. Algebraically, analytically, it looks like this. F of negative x is equal to f of x. You need to write that down because they ask you questions of this, and you need to realize that they're talking about y-axis symmetry. So what is this saying? This right here is saying if you plug in a negative x into the function, you're going to get out the original function. If you can plug a negative x into the function, you're going to get out an original function. And just let me give you an example of what I mean. F of x equals x to the 4th minus 3x squared minus 8. Okay? If I were to do this part right here, if I were to plug a negative x in everywhere I see an x, plug a negative x everywhere I see an x. So right here at this x, I'm going to put negative x to the 4th. Minus 3 times negative x squared. and then minus 8. Well, what happens when you raise a negative to a fourth power? Like negative times negative times negative times negative. Well, any even amount of negatives will always make it go back to being positive. And then minus 3, what if I took negative x and I squared it? Well, again, you have negative x times negative x. That's positive x squared. Minus 8. Hey, wait a second. I just went back to the original. That's the original function. So if you can plug a negative x in and you get out the original function, you have a function that has what's called y-axis symmetry. Now let's just look at it on our graph because I think it's also important that you can see this visually. So if you go to y equals, and we type x to the fourth minus 3x squared minus 8, zoom 6. It's coming, it just takes a while. There we go. I'm off of it a little bit. Can you see that W shape? So if I were to graph this, I would have something like, does that have symmetry along the y-axis? Here's the y-axis. If you don't know what symmetry means, you should. It's kind of like, can I fold it right along that y-axis right there? And will this side lay on top of that side? Like a butterfly, if you think of it. I don't know if you remember, like, I always remember this in kindergarten, like I put paint on one side and then you fold it and you got the same thing on the other side. So if I have this line here, do I have its mirror image along the y-axis? Yes, I did. So this right here has y-axis symmetry. We proved it algebraically, and then we also looked at it in a graph. Now, do you have to do it both ways? I think so. I think they might ask you, like, to show it. I can't remember how they're going to show it algebraically, but I mean, for sure, you can plug this into the graph and look to see if it flips over the y-axis. So that's the first type of symmetry. Obviously, if there's y-axis symmetry, there should be x-axis symmetry. X-axis symmetry. And x-axis symmetry, let me give you an example, would be x plus y squared equals 2. So x-axis symmetry, you should be able to plug in a negative y and then get out the original function. Plug in a negative y where you see a y, I should say, where you see a y. Plug in a negative y where you see the y. So this one, if I algebraically plug a negative y where I see the y, would I get out the original function? Well, again, here's that concept of squaring something. Negative y squared, negative y times negative y becomes y squared again. Oops. Well, look at there. I've got the original function. So let's go back. For y-axis symmetry, you had to plug in a negative x into the x, and you got out the function. For x-axis symmetry, you have to plug a negative y into the y and get out the original function. This one, they would actually draw it for you because you don't know how to do this part yet, but they would draw, it's actually a sideways parabola. And you'll see this is the x-axis, this flips over the x-axis perfectly. This half mirrors this half. So that has x-axis symmetry. y-axis symmetry, x-axis symmetry. The third one, probably my favorite, origin symmetry. Symmetry about the origin. And this is the little formula they use. They say f of negative x. So if you plug a negative x in for x, you get out the negative function. So again, you plug in a negative x wherever you see an x. And then this half is saying, okay, then you get out the negative or the opposite of the function. Every sign has changed. So let me give you an example of origin symmetry. F of x equals x cubed minus 4x. So algebraically, if I plug a negative x in everywhere I see an x, and I simplify it, I should get the opposite of the original function, the negative of it. So let's see, negative x for this x, cube it, minus 4 times negative x. Well, negative x cubed means negative x times negative x times negative x. 3 negatives are still negative, so it's negative x cubed. Negative 4 times negative x is positive 4x. That is the opposite sign for each of those terms, which means that the function itself is negative. Now, here's what this looks like on the graph. And this is pretty cool. X cubed minus 4x. Give it a minute. There we go. Okay, so if you notice, it goes like this. First of all, it goes through the origin. That's important. You can't have origin symmetry if you don't go through the origin. That makes no sense. But this is how I tell my students to remember it from a graph. So if you put it into your graphing calculator and you pretend you put your, as much as he can do, hon. If you put your pen at the origin, pretend your pen was standing like right here. It's hard for me to do right there. And you flip it upside down. Does that look exactly like it did originally here? Just go 180. Doesn't that look exactly like that? That means it has origin symmetry. Or if you're doing it from paper and you put your pen right here and the calculator's in the way, flip it upside down, that looks exactly like that. That's called origin symmetry. Okay, so y-axis symmetry, origin symmetry, and x-axis symmetry. Now, I hate to do this to you because we just went over all this. Now I'm going to give it new names. Why do they do this in math? I have no idea. But mathematicians decide, oh, now we're going to change the name of it. And you're like, why can't we just stay y-axis symmetry? Why can't we just stay origin? Because we have to give it new names. So there's this idea of what's called an even and an odd function. Even, odd function. And here's how I tell my students to remember. Look at the word even and take the V and make it look like a Y. If you are an even function, you have y-axis symmetry. Meaning, again, your f, if you plug a negative x in, you get out the original function. has y-axis symmetry. Odd, see that O right there? Odd is origin. Odd has origin symmetry. Meaning, if you plug a negative x in, the function comes out negative. Even, odd. Now, there is no name for x-axis, so don't worry about it. If they ask you tonight on homework, if they say, is this function even, they're saying, is it flipping over the y? Is this function odd? Is it flipping? Is it origin symmetry? Can you turn it upside down? If they ask you if it has x-axis symmetry, again, you would have to look at a graph. They'd have to give you a graph for you to actually see if it has x-axis symmetry. There's no special word there. Sometimes they may ask you, is it even, odd, or neither? Even if it has x-axis symmetry, you'd say no, neither, it doesn't have it. So we're going to do just a quick few examples of this. Determine, and I'm going to teach you some tricks right here. If the function is even, odd, or neither. So we don't need to worry if it's got any other symmetry, but is it y, is it origin, or is it neither? Meaning it's not going to flip over the x-axis either. And let's just do, let me write a bunch of them out. Y equals 8x to the 4th plus 3x squared minus 5. Okay. We'll start with this one. Now, it will get just time consuming on homework tonight if you were to just punch these all on the calculator. I mean, you could, but honestly, out of all of these, there's only one that I'm going to punch into the calculator just to double check. Every other one, I'm going to teach you a trick for. And it goes along with this idea of even and this idea of odd. So here's the trick. It's pretty cool. If every single exponent of the x is even, now these two are even right now, but I don't know if you know this, but there is an exponent to x when you have a number all by itself. You would actually write x to the 0. If a number's by itself, you have x to the 0. Hint, hint, hint. And 0 is considered even because it's 2 away from 2, kind of. So if all of these are even, take a wild guess which type of symmetry this has. This is an even function. It has y-axis symmetry. So this one is even. What about part B? Hold on one second.
He did 2 other, he did all those.
Good. Put a little check at the bottom.
He didn't miss one.
He didn't miss one?
All the way up to here.
Then he'll get tested on it tomorrow. So just put a little check and like initial it itself.
I mean, he's done everything up to 2, 5.
That's fine. That's good.
Keep going.
Without a problem, he has to do it within 3 seconds.
He did them boom, boom, boom.
That's good.
Yeah.
Sorry. My son needs to know his sight words. It's fine. He can be in here. Okay, y equals 6x cubed minus 9x. So the exponent of this x is 3, which is odd. The exponent of x all by itself is, hopefully you know this, has a 1, which is also odd. If all of them are odd, take a wild guess. It's odd. This has origin symmetry. And you can plug it in. You can plug it in your calculator and turn your calculator upside down. It'll do it. I mean, if you don't believe me. How about this one? This has an exponent of 2. This has an exponent of 1. Yeah, you can't have even and odd. So this is neither. Now, are they going to ask you if it's x-axis or anything? No, I'm pretty sure for this section, they're just going to have even, odd, and neither. Hey, buddy. Yes, Daddy. Okay, for this one, dude, give me 5 minutes. I got to finish. Okay, this one you can't do the trick with. You can't, the trick only works with, it's like a polynomial looking like this, like 6x cubed minus 9x, blah, blah, blah. If it's got like 1 over the absolute value of 3x, that one I would definitely look in my calculator just to see what it's doing. So again, I would type, if you don't know where the fraction button is, I think I've shown you before, I think it's alpha, I have to always remember myself, window, and go over to frac. And then you can type 1 divided by, to put an absolute value in here, again, you have to go math num abs. Math num abs. And then put 3x, 1 over 3x. And then hit graph. Well, there we go. Kind of looks weird. But what kind of symmetry does that have? Is that flipping over the y? Is it flipping over the x? Do I turn it upside down? No, that looks like a, crater, and this looks like a volcano kind of thing. But it does look like it's flipping over that y-axis. This half looks like the same as this half. So this is actually an even function. It's flipping over the y-axis. All right, and this one again, you can easily do, for this one, this is a polynomial. It's nothing like that. Plug in your calculator if you don't feel like it, but if you remember, any number by itself has x to the 0 power. This is odd. This is even. Can't be odd and even. So you write neither. Well, you could be an odd even function. Let me say that again. But you can't be odd and even exponents to be considered even or odd. You have to be all even or all odd. All right. Almost done. I know this has been long here. Goodness, yes, 54 minutes. We can do this though. This one, they're going to give you y equals f of x on the right side. And you have to complete the following conditions. And I wanted to show you this because I saw this on the homework tonight. So they're going to give you a picture like this, and it's going to be on the right side. And then they're going to give you 2 conditions. They're going to give you this guy and this guy. Okay, so which one meant flip over the y and which one meant origin symmetry? Meaning if I turn it upside down, it looks exactly like it is. So if you plug in a negative x and you get out the original function, this is even. Remember, it flips over the y. So I'm going to draw this as if it flipped over the y. So I'm going to draw it like that. And that's what they're going to expect you to do. I can't remember if it's multiple choice or if they actually want you to put in some points. But they just want to make sure you flip that over the y-axis. This one is odd. This one is going to be odd. Let me change colors real quick. No, this is a terrible highlighter. We'll do this one. Okay. So odd, I know this is weird, but odd is, again, you put your pencil here. If you turn it upside down, it would look like what the original function is. So odd would be like this. Let me see if I can draw it. Yes. And again, I think you have multiple choice answers for this, but if you put your pen here and you flip that, wouldn't that look like the entire shape, the original? So that's going to match up with this one right here, which is odd. So I saw that and I just wanted to make sure I went over that with you because I thought that was kind of different kind of question that they gave you. And then there's one more. They gave you a table, and I'll write it out for you, x and f of x. And they give you a bunch of numbers, -3, 10, -2, 6, -1, 3, 0, 0, 1, -3, 2, -6, and 3, -10. And they ask you, based on this table, based on the table, is it even, odd, or neither? Okay, so I'm kind of looking at things like off of what we have up here. So if I plug in let's see, if I plug in a f of 3, I get out -10. And if I plug in the negative of that, so here's right, that's what this is saying, 3, -10. If I plug in f of -3, I get out, according to this table, +10. So it looks like I'm getting the opposite of what I originally had. So then this would be an odd function. If I plug in a negative of what I had, so this is if f of 3 equals -10, and I plugged in the negative, I got out +10. And that's what it looks like is happening the whole time. You're plugging in the opposite sign, you're getting out an odd answer. So I just thought that was kind of interesting, a different way of doing another problem that you'll see on my math lab. Okay, goodness, that was a lot. But that's exactly all of what homework number 4 is. Oosh, that was a lot of writing here. So